So in this part, we will continue to cover other aspects of mean field game theory. In part one, the materials have been organized mainly around this diagram. Okay. So this is the big picture for the whole theory. Indeed, yesterday, almost everything had been tightly organized, okay, surrounding this frame. Now, let's briefly review the case for nonlinear models. Okay. We know for nonlinear diffusion cases, there are two approaches as displayed in the fundamental diagram. Okay. One is to formalize a special stochastic optimal control problem, then do a fixed point analysis. There is another route by Leslie and Leon. They solve the n-player game formally, okay, then try to check what happens when the number of players goes to infinity. Okay. So eventually, they obtain the limit as the equation system here. Okay. So let's have a look at the two objects. The first one is basically a dynamic programming equation. Okay. Here H is the Hamiltonian for the control problem. Lambda has a simple interpretation, that is the long-run average cost, because they consider an infinite time horizon, okay, optimize some sort of average. Here, nu is called the differential cost. Okay. This arises in control problems with an infinite horizon, okay, when you apply an ergodic cost. Okay. At this point, we can see, okay, we actually have all this stuff to decorate the frame. Okay. You can go either root 1 or you go root 2. Okay. It's quite complete. It's worth to have a little bit detail for root 2, okay, for the blue root when we have a nonlinear problem like this. Okay. Here, for illustration, I use the stochastic differential equation. If you do not like, it doesn't matter. Okay. You can imagine a difference equation. Okay. So that means if you introduce a model like this, difference equation, for instance, the dynamics t plus 1 is equal to t plus, for simplicity, just take a constant, then w I. Okay. You can just replace the continuous time model by a discrete time model. Okay? And the whole idea here can still be implemented. Some people may fear that if we want to do mean field games, we need to learn Ito's calculus, okay, stochastic integrals. We do not really need that. Okay? The theory is very flexible. You can choose different kinds of models. Given the dynamics and the cost here, let's check what we can do. Okay? We need to construct a limiting optimal control problem. Okay? So here we introduced this kind of optimal control problem, okay, in place of the original game. So how this can be done?
Can you go back on the slide?
Yeah, sure.
So the top equation in the instantaneous variance and then in the bottom equation of cost, you've got the sum over J.
Yeah.
J. What's the motivation for that?
Yeah, so on the previous page, we have this kind of a summation, right?
Yeah.
With respect to J, indeed, we have that. Then now, here for this optimal control problem, we no longer see that kind of J. This is actually the key point. What we do here is to use some kind of aggregation. Okay, so let's check what happens here. We know in the original model, you have a lot of details. Okay, you do summation for J from 1 to n. Okay, it's also true for the discrete time version. You have a lot of stuff. So this actually depends on the population size. Okay. Now what we want is to get something population size free. Okay. That's a conceptual move. Okay. Otherwise, each time you need to do something depending on the actual population size. That's too much. Okay. So the question is, can we introduce something more universal, okay, not depend on the population size? Okay, so here is the move. We have a little bit notation. Okay, we know in the original problem here, it's quite messy. Okay? You add up a lot of things. Now you get this notation with brackets. Okay? Many people like to use this kind of short notation. Okay? It means for the original function, okay, you average with respect to the last entry. Okay? You do integration. This is how you use the measure, okay, the probability measure, when you determine the bracket part. Okay? So it's really some kind of averaging with respect to the measure. Okay? Let's check why this works. The illustration is quite simple. Okay? Let's think of this. Okay? I say I have sigma, a function g x j just a summation. Okay, you can think of a sequence of particles. Okay, say here you have x1, x2, j. Okay. This is summation. What we want is to rewrite okay, according to some kind of integration using a measure. Okay. Given the sequence of particles, we can say consider, okay, take n equal to 3. We have 3 places. Okay. We can call this a particle configuration. Okay. It tells you the positions of different particles. Given the configuration, now we can introduce an empirical measure. Okay. So this can determine, following our notation, we can write the empirical measure. Okay. And we can further visualize by writing the CDF. Okay. This can be denoted by the CDF. Okay. Actually, an empirical CDF. Okay. Now let's check what we can do with the summation. So the summation here is really an integral. Okay. So this is the trick. For the original summation, you convert into some kind of integration. Okay. So now in the end, if somehow the empirical distribution can be approximated by a measure here, okay, without depending on n. Okay. You use this to approximate. Then in the end, you can rewrite using the integration with mu t. Okay. And for the original function, we know we have 2 other entries, okay, xi, ui. Okay. But here for our region, you really just do it with the last entry. Okay. It's like what happens here when you have a single argument. Okay, you just do integration like this. Okay. So this is the whole idea. As long as we can introduce this mu t object for approximation, then we can get rid of this very messy stuff. Okay. So definitely this is neat. Okay. Yeah, it's very compact. In the end, we can do that for the vector field F, okay, and also the diffusion part, okay, for the volatility part, and also for the integrand. Okay, we know in the original model you have the sigma part. Okay, so now it is replaced by L brackets. Okay. So that's the trick. Now let's check what's the interpretation of the 3 objects, F, sigma, L. Let's check L first. Okay. For let's check F. We have this object. Okay. Actually, we can interpret differently. Okay. What you do is to regard it as another function. rewrite. You just have the time argument. Okay, so this is like, say, is from n by, say, n1 by so by this interpretation, it's just a standard vector field. Okay? It's not autonomous. It depends on the spatial variable, time, and also the control. Okay? So under this interpretation, now what you have here is just a completely standard stochastic optimal control problem. Okay? There is nothing new. Okay? So given the stochastic control problem here, then we can use standard tools to look for the optimal control. Okay? So what we have is just to apply dynamic programming to solve this problem. Okay? And we get the HJB equation. By looking for the minimizer here, we can come up with something like this. Okay? So this is actually feedback control law. Okay? After we get the feedback control law, let's check what we can do. Okay? Let's just plug in to the limiting control problem. Okay? So we can write so now we get this equation. Okay. Previously, we just suppose this mu t has been given. Okay. So you have the original mu t, and now you just plug in to generate the random process. Okay. This is what we have here. For this case, actually, we drop the index of the agent. Okay. We can write in this form. Actually, we need a small change. This should be x sub t. It's the actual random process. Let's check what we should do. Previously, when we introduce the fixed point approach, we know we need to find an additional equation by using the consistency condition. Okay? So that means actually we need to find the a missing equation for this mu t. Okay? Let's check what happens here. Okay? And the interesting thing is that we can finish this task by using this SDE. Okay. What we do is to interpret this equation as a Minkine-Vlasov stochastic differential equation. It means here, in this equation, okay, somehow we have the driven effect of this measure-valued function defined from 0 to capital T, okay, for the vector field. In the end, the law of this process should agree with the measure mu t is assumed at the beginning. Okay. So this is the conceptual development here. Okay. So you put essentially an additional constraint. Okay. You need something for this mu t. This mu t is not arbitrary. Okay. It's intrinsically determined by the closed loop state process. Okay. The idea here is actually quite similar to the linear quadratic case. Okay. Although technically it's a little bit more complicated because now we need to directly deal with a measure-valued function on 0 to big T. Okay. In the papers, we can call this the measure flow. Okay. You can think of a measure-valued flow, okay, generated by the stochastic dynamics. Okay. So this is how we can derive the two equations for the nonlinear case. Okay. One is a dynamic programming equation for optimal control. Okay. The other is just a mechanism for us to propagate the mean field. Okay. It tells us how the mean field evolves with time. Okay. So this is the solution for the nonlinear case. Okay. In the work of Leslie and Leon, they took a different approach to derive two equations. For their case, the second equation takes the form of a Fokker-Planck equation. Okay. But actually, the Minkowski velocity of SDE is like a probabilistic version of the FPK equation, the Fokker-Planck-Kolmogorov equation. Okay. So in some sense, the two roots are equivalent. Okay. So now for the next part, just to illustrate the theory, the nonlinear theory, let's work out a more applied problem. Okay. This is called stochastic growth with relative performance. Yesterday, I described this as an example, okay, to show the idea of mean field modeling for growth problems. Okay, so a few words about the modeling here for the growth problem. Since we will use relative performance, it's good to give a little bit background for the economic literature. Actually, there is already some history of this kind of performance measure. It's also used in mean field games. In the recent work, I think this one is published in Math Finance. For this work, they actually use a geometric Brownian motion to model the dynamics of risky assets. So you have the stochastic processes for the assets. Also, they introduce the performance. Okay, let's check what it means here. So this is basically the utility at the terminal time. Okay. The optimization is done on an interval from 0 to t. What you care about is how you perform at the terminal time. Okay. So here, each random variable is for capital T. Let's check what it means. So the first part is actually your eyesight, okay, at the terminal time. Here we have the convex compilation with another term. Okay. The interpretation of this term is quite obvious. Okay. It tells us on average how well all other guys are doing. Okay. So you calculate their average eyesight, and then you check the difference. Okay, figure out the difference. You can see if you are better than the average, okay, then you will introduce something additional positively into the utility. So if you are better off than the mice, you are happy. Okay. If your performance is much more above the average, you are much more happier. Okay. There is a good reason to use this kind of modeling. In the economic and financial literature, there is some argument about using this kind of performance. Okay. For example, in the financial sector, okay, if you are a manager, for this year it's quite bad. Okay, say the return rate is like 1%, okay, quite bad. For your peers, okay, like all other managers. So if you achieve, say, 1.5, then you're happy. Okay? You can easily report to your boss. Okay? Yeah, the whole crowd is not doing well. Okay? I'm better than them. Okay? Yeah, you're okay. Also, you can think of another scenario. Say, for this year, the average performance is like 15%. Okay? For you, you achieve, say, 80%, you will get some problem. Okay? Other guys are doing better than you. So that's why it's well motivated to consider this kind of relative performance. Okay? So this is a little bit background. And now we just recall the model we introduced yesterday. Okay. The dynamics are quite standard. Okay. You have your own capital stock, okay, and your own consumption. So in this case, CTI is the control. Okay. It takes the form of consumption rate. Okay. And we also have some interpretation about the Brownian motion part. Okay. It can be related to stochastic depreciation. There is no coupling through dynamics. Okay, so the growth part is like independent. Okay? If you assume the control part is already independent, so you have nothing to do with other guys. Now for the next part, we introduce the utility. In this case, we actually have the relative performance, okay, because it's based on geometric mean of your own utility. Okay, we know for the consumption rate, you put gamma, the exponent here, we have the interpretation according to utility. And the second part is like the ratio of your own utility to the average of the population. Okay. So in the end, we just get the weighted geometric mean for two components, okay, U0 and U1. So we have the performance metric. This is a game, okay, because if you participate in the in this model, definitely you just care about yourself. Okay. So this is really a non-cooperative game. If we follow the traditional approach, okay, you will immediately get big trouble with complexity, okay, when you compute. Okay, yesterday, for a stochastic control problem with a state space in R4, okay, I have shown that the computational load is already very big. Okay. So now if you consider I marked like, say, 20 players, there is no way to do it numerically. Okay. So it's really important to use the mean field game approach to try a solution. Okay. Let's check what we can do. We can recall the fundamental diagram by the fixed point approach. Okay, we know a key thing is to introduce something to approximate the aggregate behavior of the whole population. Okay. In a general setting, we need to introduce a distribution mu-t called the mean field, okay, to capture the aggregate effect of the population. So it's important to introduce something here to approximate so that we can formalize an optimal control problem. Okay. So now we just implement the idea along the red route. Okay, so for the original model, let's do something with the utility function. Okay, we know in the original utility function, we have a lot of coupling, okay, between yourself and the population average. What we do here is to propose a deterministic curve, okay, to approximate this term. Okay. So this is the first step, Ct and gamma to be approximated by a deterministic curve. So why here we do not introduce a more general measure valued function? The reason is that for the mean field coupling part, okay, we have this kind of average. Okay. By the law of large numbers, it should be enough to approximate this average by a single value, a constant. Okay. Now, if you have different t, eventually you produce a curve. Okay. So that's how we can approximate by a deterministic curve. In the end, that deterministic curve, okay, it's denoted in this form. Okay. The superscript is just a matter of notation. Okay. We know here it's assumed to be a continuous function, okay, defined on 0, t. And the function is positive because in the approximation we are dealing with the average here. Okay, consumption rate should be positive. I cannot say today I consume minus $40. Okay, you cannot do that. It's for a positive object. It makes sense to have the restriction. Okay. So once we assume this was already known, okay, we can see that it's just a standard optimal control problem. Okay. You have your own state. Okay. Here we drop the superscript I. Okay. And you have your own utility. There is no longer interaction with all other guys, okay, because you just assume this object is already given. So you have an optimal control problem. Then we try to find the optimal control CT. Okay. After we get that, this is called the best response. The next part is to imagine, okay, all other guys are doing the same reasoning. Okay, so they also separately figure out their best responses. So everybody does the same. Then we can imagine, okay, their closed loop will regenerate something. Okay. Actually, we require that they regenerate the same deterministic curve. Now, the word question again. Okay. Initially, we just assume C bar gamma were already given. In reality, it's not. Okay. So we need to find the missing equation, and we do that by applying the consistency condition. Okay. So that means if you average all the individual closed loop states, okay, you should regenerate this deterministic curve. Okay. That will provide us a fixed point equation. Okay. There is a little bit detail. We do not need to go through that. Okay. But conceptually, it's easy to understand, okay, as long as we follow the right route. Okay. So take it for granted, okay, that eventually we can come up with a fixed point equation for determine the deterministic curve. Okay. Technically, we do a little bit change of variable, okay, in order to make the equation look better. Okay. So we actually define this quantity big B, then define little b again. Okay. So from C we go to B, then to little b. And eventually, if we formalize the fixed point equation, we can write in this form. We know here little b is a deterministic curve. Okay? If you have an operator, you should directly act on the whole curve. Okay? Finally, for the new curve, you evaluate at little t. Okay? That value should agree with the original b little t. Okay. So this is how we can set up the fixed point equation. Okay. We have a little bit of notation. This is how we can get the equality, okay, according to the fixed point operators. the interesting thing here is that at one stage, we need to calculate the mean of this term. Okay. So it seems that eventually we still need to use the distribution. Okay, we need to introduce the Fock-Planck equation. But the good news is that we can actually determine a linear equation for this function of time t. So that's nice. You have some kind of closed list. You can analytically calculate this term. Okay, if some other related functions are already determined. Okay. So in this case, you can actually avoid directly computing the Fock-Planck equation. That reduces the computational load. Okay. What you do for the fixed point equation is just to iterate in a space of continuous curves. Okay. That's definitely easier, okay, than iterating a surface. Okay. Okay, so this is how we can get the fixed point equation. Okay. And here I suppose somehow, okay, we have already calculated the solution to the fixed point equation. Then next, we can figure out the consumption strategy. Okay, so you can see this is actually a linear feedback. It's very neat. Okay, what you need to know is just your current capital stock. Okay, then you have the feedback gain. Okay, so it tells you what's the fraction you need to use, okay, for the consumption. Here actually it's a consumption rate. Okay. For implementation, you do not need to check your past history. Okay, I don't need to have a book to keep the past record. Okay, what I need to know is my current capital stock. Okay, then I can implement the strategy. Okay, so this is definitely a low complexity control strategy. Okay. Then following the fundamental diagram, we need to decide if all guys, okay, all the n guys apply this side of strategies, what we can say about the performance. Okay, so what we have is actually an Ibsen-Nash equilibrium theorem. Okay. The first part is the technical component. It tells us the quality of the mean field approximation. Okay, we know the actual population average utility is random. Okay, we try to use a deterministic function to approximate. Okay. This tells us how good the approximation is. Okay. And now for the Ibsen-Nash equilibrium theorem, what we have is if you try to improve, okay, you try to deviate from the given set of strategies for yourself, okay, you try to improve, but you cannot really improve too much. Here we use soup. The reason is in this problem we are dealing with utility. Okay? If you talk about utility, you try to get it bigger. Okay? And we have some numerical simulation, actually numerical computations. So here is the illustration. Okay. We try different values of lambda. Okay. Lambda tells you how much you care about the relative performance. Okay. We can go back to have a look. Okay. Okay. So this is the exponent for the relative performance part. Okay. If you choose different lambda here, that will impact your solution. So for different lambda, we can check the solution of the fixed point equation. Okay? And also, for this term, we have the control gain. Okay? You can see when it's near the end of the time horizon, you consume quite rapidly. Okay? The reason is that in this model, we just put a very small weight to the terminal part. In the cost structure, we take a very small value for this epsilon to regularize the behavior of the players. So that means it's not so important. In the end, when it's near the end of the decision horizon, it consumes very quickly. So you can imagine, say, now I'm near the very latest stage of my life, okay, but I still have a lot of money. I try to consume as much as possible. Okay? I try to buy very expensive cars and so on. You can imagine. But this is a very typical phenomenon in different optimization problems, for example, about portfolio optimization and so on, okay, when you optimize portfolio consumption and so on. And here we have the illustration of the solution for the fixed point equation. Okay, we know for this deterministic curve, okay, it's a function from 0 to 2. Okay, so you have a curve hang above this interval. Now, if you iterate, you will move in the other direction. Now, in the three-dimensional space, by the iteration, you just generate a roof, okay, on your above the ground. Okay, so you get this roof. You can see the convergence is quite rapid. Okay, so that's one application of mean field control, mean field games for a growth problem. Actually, in the literature, we can also see applications by other authors. Okay, for example, for portfolio optimization problems. The next part is about a generalization of the basic theory. Okay. For the lecture so far, okay, we actually stay very close to the fundamental diagram. Okay, we don't want to deviate too far away. Okay. Now let's try to move away from that framework. What we can do if we generalize? A very natural thing is to consider a major player. We know in the previous models, okay, we have just peers. Everybody is comparably small. Okay. Now you can imagine we have a very big guy. Okay. Then the structure of the model will change a lot. Why we consider this kind of problems? You can imagine financial markets. Okay. You have one institutional trader, okay, then a large number of smaller traders. Then you immediately have a situation like this. Okay. Indeed, in the mean field game literature, now some researchers have used this kind of framework, okay, to do optimal execution problems. Okay. For example, the work of Jamanga and Lorian. Okay. So let's check what's the idea of introducing the major player? We basically have two parts. Okay? One is the equation of the major player. Okay? It has its own state, own control, then the average of the smaller guys. Okay? And then we have the equation for the minor players. Okay? Why we have this difference of a major player and the minor players? The reason is that for this guy, okay, with index 0, you can see it appears here. Its coefficient is like big O 1. Okay? We have a constant coefficient. That's a very big influence on other people. Okay? If you check a minor player, it's different. Okay? Their mutual impact is very small. Also, if I'm the minor player, my influence to the major player is also small. The reason is that for my state, okay, in front, I have the scaling coefficient. Okay? So if I'm a small guy, I cannot affect A0 too much. Okay? So there is the difference of the powers of the players. Okay? In the traditional literature of cooperative games and the static models, okay, we have this kind of structure. Okay. So now what we do is to generalize to mean-field games. Okay. Actually, we can consider non-uniform minor players. Okay. They can depend on their individual dynamic parameter. Okay. In this case, we need to generalize the theory. Okay. A very important feature is that in this case, we do not have a standard law of large numbers. Okay. Here we have this average, but you cannot really immediately use the law of large numbers. Why? Because you receive the influence from the major player, okay, non-trivially. Okay, you receive quite big influence from W0. So eventually, all the minor players have very strong correlation. Okay. If you average in the end, the limit is still random. So here, somehow, we end up with a random mean field. It's very different from the previous modeling. For standard mean field games, in the end, what you have is a deterministic thing, okay, to describe the population. But now you cannot really repeat that. Okay? The mean field will be random. We also similarly introduce two types of cost. Okay? One is for the major player, the other is for the minor players. Okay? In this case, the major player has strong impact on other guys. Okay? Now let's check how we can solve this problem. I will not go through all the detail, okay, but I will explain the intuition behind the solution. So basically, at the end, we face a matter of sufficient statistics. Okay. Probably you could guess, okay, that for the major player, it's enough to know its own state. Okay. For the minor players, it's enough to know the state of the major player, also the state of the minor of itself. Actually, it's not true. Sometimes intuition is not reliable. Okay. In order to solve this problem, what we need is to do a little bit expansion of the state space. Okay. You introduce another object, Z, okay, to describe the population average. Okay, so basically here, if we just consider a single class of agents, okay, if then ZT is roughly just the mean field, okay, formed by the Miller players. This is the interpretation of the Z component. Okay, eventually you can obtain this kind of strategies. Okay. This model can be generalized in many different ways. Okay. First, here the parameter can be from a continuum rather than from a finite site. Okay. In the end, the analysis is quite different. Okay. Yeah. There will be some complication. Okay. And also, nonlinear models, as done by Laurent Keynes, Kamala, and some other researchers, including Professor Ben Susan, and also the work of Bogdan and so on. Okay. It's an increasing literature on this kind of major player modeling. And here I will mention another interesting aspect. Okay. Actually, for the major player model, it's possible to consider leadership rather than just large games. Okay. So you have a very big guy as the leader of the optimization problem. Okay. Eventually, you can formalize kind of Stackberg game. Here I will also mention other collections. This model, the major player model, is actually closely related to the so-called common noise model introduced by Lyons in his lecture. It's probably around 2010 by the survey people because its lecture is not a published paper at the beginning. So we need to check this reference for detail. Another thing is the master equation for mean field games. Okay. So far, for the solution of this kind of problems, okay, we essentially come up with two equations. Okay. The optimal control equation and then mean field dynamics. For major player cases, okay, you have a little bit of variant. Actually, there is another way to approach mean field games, that is to consider the so-called master equation introduced by Lyons. Okay. The idea is to just use a single equation to describe the solution. It can be viewed as some kind of abstract dynamic programming equation. The next extension is to consider social optimization. Okay. Previously, we assume everybody is selfish, so they solve non-cooperative games. Actually, there is a good reason to consider cooperation. Why? We're thinking of this. Say, electric load management. In large apartment buildings, okay. You suppose in each unit you have some kind of deferrable loads. Okay, say air conditioning, space heater, and so on. Okay. If you delay your usage, it's okay if you delay it a little bit. So it makes sense to consider a control problem, how to do it smartly. The point is that, say, now you have the big apartment building. Suppose it's for the same owner. Okay. You have a very big building. It's owned by the same boss. Say, it's me. I'm the owner of this building. For the optimization problems for individual apartments, certainly we can do it cooperatively. I want to say save energy, save bill, and so on. Okay. Anyway, I'm the boss. Okay. I care about a single objective. So the idea is for the optimization problems of different apartments, we can aggregate the objective into a single one. So it makes sense to consider the so-called social optimization problem. Okay. Here is a conceptual model. Let's start with the linear quadratic case. Okay. We have very simple dynamics and also individual costs, okay, coupled through this average term. We also have a little bit notation here. W means the noise. Okay. The social cost is defined as the total of the individual costs. Okay. Now the question is how to minimize. Okay. What we want is to find some sort of Pareto optimum. Okay. Probably you would say this is just a standard optimal control problem. Okay. Why not just look for a solution from textbook? The point is that we cannot do that. If we rewrite, okay, say form a big state vector, optimal control problem, we form big state, okay, x1, xn, you then optimize G as a function of U. By following the standard optimal control theory, you will get a problem, okay? Because what you get is centralized control. Okay? So, for example, for this room, we have the control unit on this wall. That means for my action, I need to collect so much information. Okay? Say if you have a big hotel with 4,000 rooms, that means you need to collect a massive amount of data for the control unit of this hotel room. It's not realistic. So we cannot really use the traditional approach. Okay. In the end, the idea of mean field approximations can be generalized to this case. Okay. And we can eventually construct a very compact set of equations. Okay. Here, theta is from the parameter set. Okay. It's allowed to be from a continuum, okay, for the dynamic parameter. Okay. And we can look for a solution to this equation system under appropriate conditions. Okay. So the question is, how is the social certainty equivalence equation system constructed? the idea is different from mean field games. Okay? The reason is that for mean field games, essentially, given the population behavior, okay, I just look for my own best response. I'm selfish. Okay? Check what's the optimal for myself. Now, for the social optimization case, you cannot be selfish. Okay? We can think of our daily life example. Okay? Say somewhere, say in a big city, somewhere in some country, road users, okay, I mean drivers, are very aggressive. Okay? They are very selfish to take advantage of the road resource. If you just care about yourself, about your own utility, okay, you are very aggressive. Okay? Take every chance to manipulate. Actually, overall, it will not be efficient. Okay? The reason is that when you just care about your own reward, you will do harm to other guys. Okay? That's actually the situation of wardrobe equilibrium. Okay? As some kind of large equilibrium, it's not efficient. So now, for the social optimization problem, the key idea is to find the right balance of self-interest or self-improvement and the social impact. Okay? So if I try to optimize to improve my own situation, you also need to check, in this case, how much damage you will do to other guys. Eventually, you need to balance the two effects, okay? And hopefully, you can find a strategy that's optimal for the whole society. Okay? And mathematically, we can formalize this according to person-by-person optimality in team decision theory, okay, rather than game theory. And in the end, we can use this kind of idea to construct the equation system. Okay. And the main result is here. Under some assumptions, we can show existence of a solution to the previous equation system. Then we can form the decentralized strategy. Okay? You only use your own state, okay? And some kind of macroscopic effect, okay? Which also depends on your own parameter, theta. Okay? Finally, we can show that by this set of strategies, okay, you can almost achieve social optimality, although now each individual just uses a little bit information, okay, about its own state, okay, and some other stuff. Okay. So we can imagine now we have a big hotel, okay, 4,000 rooms. We want to do the social optimization because I'm the boss. Okay. I'm very rich. I run this big hotel. In the end, by this methodology, for the control, say we have the control unit on the wall. What you do is to use your own room condition and then some macroscopic information, say, provided by the network. Okay. You just use a little bit information. That's enough. So it's a very big saving of information. Okay. You do not need to measure the room temperatures for 4,000 rooms. Okay. So this is social optimization. And now at this point, we can return to the previous question in part 1. That is, how we can address efficiency loss in mean field games. Okay. In the recent literature, this is also done by some other researchers with different models, including nonlinear models. Okay. Now, for the linear quadratic case, actually we can check the social cost per agent. Okay. Here we have the parameter. We know in the model we have a parameter indicate the strength of the coupling, okay, between the individual and the population. For the social optimization case, okay, we can calculate the cost, okay, according to different coupling parameter values. For the mean field game, we can also do that. Okay, the interesting is that for the mean field game, at some point you will explode. The problem is not soluble if gamma is too big. Okay, so we only have this range. And we can check the difference of the two optimization methodologies. You can see the social optimization case will do better. Okay, you have some cost difference. Okay, if you make the difference of the two curves, okay, then you can display here. So basically, when gamma is very small, it's quite small. The two approaches have similar costs, okay? But when gamma is relatively big, you start to get this big gap, okay, for the cost. Okay? So this is how we can address efficiency in mean field games. And here is another very basic question. Okay? I just figured out this with Corso recently. The question is, what's the relation of the two approaches in the fundamental diagram? We can have a look at the diagram here. Oh. Yeah, so given a model, in principle, we can try two different approaches. Okay. So far, for different concrete models, we got the impression that they are actually equivalent. Okay. But we need to be careful. Okay. The point is that so far, we solved different problems under different sufficient conditions. Okay. So we cannot be quick to claim that they are actually equivalent universally. Okay. We need to be careful. So now the question is there a way to detect the difference of the two methodologies? The answer is yes, but we need to do that properly. Somehow, this is, this answer is kind of overdue. There is a good reason to not have such an answer in the past. The point is that in the past, we started different problems, okay, with different sufficient conditions. Also, for the direct approach, it's very hard. Okay? It's a very hard problem. Typically, you put quite strong conditions on the model. Okay? So eventually, you cannot see the real difference of the two approaches. Here, in order to answer this question, we need to take a good strategy. That is, we introduce a specific class of models. Okay. Here, actually, we take the linear quadratic class, then try two different approaches. Okay. Then we will obtain some models to indicate the real difference of the two approaches. Okay. You can imagine this. Okay. Say here in this room, we have 30 excellent top high school students. Okay. They are enrolled into a very competitive program. The issue is that we cannot really differentiate them too much. Okay. We want to ask who is really better. Okay. So in this case, you need to carefully design a device, okay, so that you can let the individuals pass this device. Then you can detect, okay, which small group is obviously better than other guys. Okay. So we need to do something to separate models. So this can be done by the linear quadratic framework. Okay. For general nonlinear cases, it's unlikely to answer this question easily. Okay. It's because the direct approach is too hard. It's hard to obtain necessary and sufficient conditions for each approach. But for the LQ case, indeed, we can achieve that. Okay. For each root, we can determine what are the sufficient and necessary conditions for their feasibility. Here, basically, we have the linear quadratic model, symmetric for symmetric guys. Okay. You have A, B, G, D, then gamma, R, and so on. Okay. So it's for a population of symmetric agents. Okay. But it's possible to give different values for this kind of parameters. Okay. So eventually you form a family of models for this class. I will skip the technical analysis. Okay. The interesting is that if we restrict to the this class of models, eventually we can indeed differentiate the power of the two different approaches. Okay. Basically, by the fixed point approach, we have this domain for the models. Okay. That means for this set of models, the fixed point approach will go through. We can also check the direct approach. Okay. Actually, we need to formalize this appropriately. Actually, we call that asymptotic solvability. The procedure is similar to Leslie and Leon's approach. Okay. You directly solve a very big scale problem, then let n go to infinity. You try to check what happens, okay, whether they will crystallize into something really simple, okay, with limiting objects. The result is here. Okay, so it means for a subset of models within the blue circle, the direct approach is feasible. Okay. So this tells us actually the two different approaches are not equivalent universally. Okay. If you want to get equivalence, you need conditions in order for them to agree. So basically, the domain of applicability for the direct approach is strictly smaller. We can also address some other issues, say non-uniqueness. Okay. Actually, for the LQ case, by the approach developed in this paper using a rescaling technique, okay, we can also determine a small set of models in which we can have multiple solutions. It can happen. So to finish, I will just display the related references. The literature is quite big. Okay, for the lecture, I just randomly sampled a small number and insert them into the presentation. Okay, if you want to find more, you can go through several sources, particularly the handbook article and the very big book by Kamara and Deralu. For the PDE part, you can consult the survey paper by Gomez and South. But somehow this is already several years ago. Okay, many new results in the PDE setting are not covered. Okay. Anyway, you can combine the whole list to see very rich literature. Thanks for your attention.
I believe we actually have run out of time, but I wanted actually just to take this opportunity to thank the organisers, Eugene and Yvonne, for a wonderful conference.
Thank you very much for your contribution. I have learned a lot, really. Hope to see you at another workshop in the future. Thank you. Yeah. Thank you. Big thanks.